So what you've noticed here is I've placed the 4 numbers from this set into L1 to help me explore. Of course, I could have done this by hand, but I don't think it's necessary. And we want to find a bunch of descriptive statistics for this. So I think you know how to do this by now. Stat calc 1 on L1, no freak list, and calculate. And there we go. And Unwan, what is the minimum of this set? -2. And Justin, the maximum? 8. Savag, the mean? 4.25. Jeffrey, the median? 5.5. Ethan, the Q1? 1. Daniel, the Q3? 7.5. Mara, the standard deviation? 4.5. And Unwan, the range? 10. Elif, the IQR? 6.5. Okay, any questions on getting those statistics or what they mean? Hopefully you know that by now, since we've studied Chapter 5. Okay. Now let's see what happens when we add 1 to all the original numbers. This is easy to do with the calculator. So I'll go to Stat, Edit, go to the very top of L2, and what should I type? L1 plus 1, very good. So second 1 plus 1, enter, there you go. And now we'll just do a stat calc 1 on L2. So Lucy, what's the min? Where am I here? So -1, 5, 8, 9. So the min is -1. Matt, the maximum? 9. Glenn, the mean? Nice job. Jeffrey, the median? 6.5. Savag, the Q1? 2. Matt, the Q3? 8.5. Savag, the standard deviation? 4.5. Justin, the range? 10. And Laura, the IQR? 6.5. Okay. So let's stop for a second. I'll go to a volunteer. What do you notice? Yes?
The min, the max, the mean, the median, Q1 and Q2, 3 are all changed by the constant?
Yes. The min, the max, the mean, the median, the first quartile, and the third quartile are all changed by that constant. While the standard deviation, range, and IQR stay the same. And Savag, why do you think those 3 things are not changing?
Because it's proportionately moving, so it's going to be the same values.
Yeah. All we're doing is shifting the distribution. We are not spreading it out more or less. So the measures of spread or variability do not change. Capiche? Okay. Now let's double the original numbers. Nice. L1 times 2. -4, 8, 14, and 16. Now let's see what happens when we double, which is the same thing as multiplying by a constant of 2. Glenn, the minimum? Good. -4. Hiji, the max? 16. Laura, the mean? 8.5. Good. Mara, the median? 11. Good. Savag, the Q1? 2. Lucy, Q3, 15. Justin, the standard deviation, 9. Hiji, the range. Say again. 20, thank you. Ethan, the IQR, 13. Okay, thank you very much. Splendid job. A volunteer, what's going on here? Matt? Everything is being doubled now, including the measures of variability. I want to also ask you, why are the measures of variability changing? Jeffrey?
This is when you are spreading out a little bit, you're making all the values larger.
Exactly. Yep. If you multiply by a number other than 1, you are either making the spread larger if it's greater than 1, or smaller if it's less than 1. Okay? So we're changing the spread. So just something that relates to this. A few years ago, one of the classes asked us to weight the decorations event in Olympics double, because they felt like they spent so much time on it and they wanted it to be worth more. They actually wanted all the morning main gym events to be worth double. But the Olympic Committee said, we'll try just this one first. Well, if you know anything about Olympic scoring, this is how it works. First place is 5.5 points. Second place is 4 points. Third place is 3 points. Fourth place is 2.5 points. And no team is 0 points. Okay, so what's the range between first and fourth normally? 3. But we're doubling it now, so this becomes 11, 8, 6, 5, 0. What's the range now? Okay, 2 times 3, or 6. So some people argued that by doing that, you increase the spread between first and fourth place, and that may not be what you want to do. Okay? So just making a connection with something that you might be familiar with. All right. Last one, we're going to double the original numbers and then add 1 to them. So in L4, I can do 2 times L1 plus 1. So negative 3, 9, 15, and 17. And we'll do the statistics there. And Unwan, the minimum, negative 3. Matt, the maximum, 17. Laura, the mean, 9.5. Hiji, the median, 12. Mara, the Q1, 3. Unwan, the Q3, 16. Jeffrey, standard deviation, good, 9. Glenn, the range, 20, good. Justin, IQR, 13. Again, a volunteer. What's going on here that's special? Daniel?
The 5-point values, also the meaning, they're double the original value, and then only 1 is added to each of them.
Yes.
Whereas the standard deviation, the range, and the IQR are just double.
Yes. Okay, that is the most important thing. Notice that the measures of variability are not being affected by the addition of 1, only by the doubling. Okay. So notice the connection here. Measures of spread stayed the same when we just added 1. Measures of spread doubled when we multiplied by a constant. And when we multiply by a constant and add by a constant, the measures of spread do not change with the addition of the constant. Okay. So I'll just sum up our learnings here. Measures of center and position are affected by shifting, which is addition or subtraction by a constant, and scaling, which is the technical term for multiplying or dividing. Think of a scalar. You may have heard of that term. If you've studied matrices, you may have heard of that term scalar, multiplying by a scalar. And measures of spread, or you can call them variability, are not affected by shifting, but are affected by scaling. Like I said, once you know this, you can be more efficient. For example, if for some reason, like on a bunch of test scores, if I decide to give everyone an additional point, I don't need to actually do that in the spreadsheet and then recalculate things like mean and standard deviation. I know what's going to happen. The mean is going to go up by 1. The standard deviation is not going to change. Okay? So it can be helpful to know these things. Good. Any questions on the first side? So let's ask you conceptual questions to see if you understand. Glenn, let's say you're a manager at a Starbucks and business has been good, and you decide that you are going to give all of your employees a $50 raise per week. Okay? What's going to happen to the average paycheck? By $50, right? What's going to happen to the range of the paychecks? It's not going to increase.
Well, the range itself, like the hours,
Because you're giving every person $50, so you're just bumping it up. So the max is up by 50 and the min is up by 50. So when you take the difference, the 50s cancel. Okay? Now, let's say that you give everybody a 5% raise.
5% raise.
Okay. What's going to happen to the mean paycheck? By 5%. Okay. What's going to happen to the standard deviation of the paychecks? By? Exactly. Okay, so measures of spread are affected by multiplication or division, but not by addition or subtraction. Okay? Any questions there? Great. Let's take a look at the back. As I said, you already have an understanding of a method of standardizing. It's called finding the percent. So I said to Ethan, if he gets a quiz back that has a grade of 28 out of 30, most likely he's going to use his calculator to figure out what that is as a percent, because that makes more sense to him. It's on a scale that he's used to. We're going to come up with a new method here called the z-score, the standardized score. And it's going to involve the mean and the standard deviation. So we have 3 imaginary competitors. They're all competing in these 3 different events, the 100-meter dash, the shot put, and the long jump. And we're told the mean of everybody and the standard deviation of everybody. Good question. Shouldn't the mean for the shot put be 63? This refers to every competitor.
Oh, this is just one competitor.
These are 3 competitors,
But there are more.
but there are more competitors. Yep. I'm really glad that you pointed that out. Okay. Okay. Safag asked, why isn't the mean for the shot put 63? And my answer was, because there are more competitors. Okay. So let's try a method that's not going to work. Let's rank them. So in the 100-meter dash, who came in first? Competitor B. Who came in second? Competitor A. Okay, and then competitor C was the slowest, so they came in third. Shot put, who came in first? A, second, C, and then obviously B came in third. Long jump, who came in first? C, followed by B, followed by A. Okay. Now, if you use these as scores, let's add them up. 2 plus 1 plus 3 equals 6. 1 plus 3 plus 2 equals 6. And 3 plus 2 plus 1 equals 6. Well, you might come away with this saying that the competitors are equivalent. But that's a simplistic conclusion, I think. Yes?
I would say that the competitors are each better at things.
I agree with you. The competitors are better at different things.
Yeah, I would say they're
I agree. What we're going to do is find their standardized scores. And what that's going to do is determine how well they did with respect to all competitors. Okay? And like I said, it's going to involve the mean and the standard deviation. This is symbolized as Z. One of the many things I do not know. Why the letter Z was used. So when you hear Z-score, this is what this is referring to. This is a simple calculation. You figure out how far the value is from the mean. That's the first step. Okay? So X minus X bar. But that's not good enough. Why? So let's say that I told you your test score was 5 points above the mean. What else would you like to know? Yeah. What the mean is? Okay. What else? Yes.
What the standard deviation.
What the standard deviation is, and why does that matter?
Because you're comparing your standard deviation to the average standard deviation. Not the average, the others, the whole standard deviation. You're comparing how far you are compared to what the standard deviation is.
Okay, and what does the standard deviation tell you?
It's like the average distance from the mean.
Yes. And why is that useful information?
Because on the top, you're calculating how far away you are from the mean, so you want to know how far away everyone else is.
Yeah, and that standard deviation tells you that.
Yeah.
Okay? So if you were 5 points above average and the standard deviation was only 2, that's much different than if the standard deviation was 10. Okay? So if you're not getting it, I'll try another tactic. So let's say the mean on a test was 80 out of 100. And the standard deviation was 5, which is small for test scores. And let's say you were 5 points above the mean. Well, in this scenario, you're only 1 standard deviation above the mean. Now, different scenario. There's a lot more variability in the scores. Twice as much. Your score is still the same. Although it's above average, it's not as good relatively speaking. Do you get that? Because there's more variability in the data. Okay? So this one is not as remarkable. Okay, yes?
For the first thing, how is it 1 standard deviation above? Because isn't like 80 plus 5, 85, and that's what the rest of them
Yeah, so aren't they 1 standard deviation above the mean?
are? Oh, got it. So it's like the multiple 5.
Yeah. I saw some looks of confusion, so let me try yet one more tactic. I'll draw something. Let's say the test scores followed this distribution. Which is idealized, but it will work for our purposes here. If the standard deviation is double, what happens to this curve? It spreads out, right? Okay. So for here, your score might be here. That's your 85. Okay. For here, though, because the standard deviation is a lot more, you're going to be like here, closer to the average, relatively speaking. Okay, so not as remarkable. If you get that, then you get z-scores, the essence of them at least. Okay? Another example. Getting an 800 on SAT Math is not as extraordinary as getting an 800 on SAT Reading. Both obviously excellent, but one is more unusual than the other. Okay? Has to do with relative performance. So what we're going to do here to account for the variability that exists is divide by the standard deviation. It's like using standard deviation as a unit of measure. You're going to ask yourself, how many standard deviations am I away from the mean? And make judgments based on that. Okay? If you're only half a standard deviation away from the mean, that's not as unusual as being, let's say, 2 standard deviations from the mean. Okay? So let's do this for these 3 competitors. A, B, and C. 100 meter shot, long jump. Okay, so for competitor A in the 100 meter dash, 10.1 minus 10 is 0.1. So they were 0.1 seconds above the mean. Not good enough. Doesn't account for variability. Let's standardize it by dividing by the standard deviation. Okay. So competitor A was half a standard deviation above the mean. Competitor B is going to be half a standard deviation below the mean. Hopefully you can see that, but if not, just do the calculation. And then competitor C is 1.5 standard deviations above the mean. That's a big deal. It's a very good performance. But I made an error in judgment. Tell me what it was. Yes?
Well, if you're like 1.5 standard deviations above the mean, that would mean you did worse. It's the 100-meter dash.
Exactly. Okay, very good. Think about what you're doing. What we might want to do here is switch the signs on these things to account for this. Okay? So I'll make this negative, I'll make this positive, and I'll make this negative. Now we can see competitor C, no, did not do well. Okay. Now for the shot put, getting a higher value is better. So 66 minus 60 divided by 3. So competitor A, 2 standard deviations above the mean. Competitor B, I don't even need to do any calculations. They got the mean, so their z-score is 0. And then competitor C, pretty easy calculation. They are 1 standard deviation above the mean. For the long jump, more is better, so we don't have to do that correction like we did for the 100-meter. Competitor A, no calculation needed. Their value was the mean, so their z-score is 0. Let's be careful here. We have a mixture of units. So what would the z-score be for competitor B? 2. Okay. Be careful with the units. The standard deviation units are inches, excuse me. And this is 0.5 feet. Okay. And then for competitor C, they were 1 foot 3 inches above the mean, or 1.25 feet above the mean, and then we divide that by half a foot because that's the standard deviation. Now let's add. So this is going to be 1.5, 2.5, that's going to be 1 and 1 and 2. Okay. Now, relative to all competitors, who's the best? Competitor B. Okay. They have the highest total standardized score. Good.